So, friction. We're going to take a deeper dive on understanding how friction works. So, what is going to determine what factors are going to determine how much friction an object experiences? How fast it's going, great guess. That actually doesn't play a part of it. Other thoughts? Friction. Surface area surprisingly actually doesn't. Doesn't. Okay. Weight in a way does, but it's not. Okay, I'll just tell you. So this is the coefficient of, so the roughness of the surfaces, like the type of materials that are rubbing. Different surfaces have different amount of friction. Okay, that's captured with this thing. It's called, the letter is mu. It's the lowercase m in Greek. Don't worry about that. We're going to say it's the coefficient of friction. This describes how rough the surface is. So sandpaper has a high coefficient of friction. That makes sense? So the rougher the material, okay? And then the other thing it depends on is normal force. And this is not solely dependent on the weight of the object, but think of it like when you're pushing something, heavier things have more friction than lighter things. That's because heavier things tend to have a greater normal force. You okay with that? Okay, so that's the equation for friction. The coefficient of friction times the normal force. Okay. All right, so let's pretend that this trash can is really heavy. Okay, and I want to push on it. But before I do, right here, so your free body diagram of your trash can, you got gravity and normal force. Okay, you can see that. Okay, you got gravity and normal force. Anything else? You need friction at this point. Nope. Okay, so I go to push on it. I'm like, and I don't move it. Sorry. Momentary repositioning of the camera. we're just going to go with it. All right. I push on it. I have an applied force. Friction is like, nope. Good with that. I push on it harder. I'm like, so the free body diagram doesn't change, except for the fact that the force is stronger. So friction acts back. Like, man. So I push harder, like, more force, more friction. Okay. So what I'm going to do is I'm going to graph friction. As I push harder, friction pushes back harder still. Okay. So as I'm increasing, friction's increasing its force. Okay with that? As I push harder and harder and harder. This type of friction is known as static friction. This type of friction, this is the friction that prevents slipping or sliding. The friction that prevents slipping or sliding. It's static, not moving. Good with that? Static friction is the friction that prevents slipping or sliding. So molecularly, here's what happens. So I'm going to zoom in on this interaction between the trash can, the bottom of the trash can, and the tabletop. So I'm going to zoom in here. The bottom of the trash can at a molecular level is super rough. The tabletop is also at a molecular level super tough, super rough. So friction comes from the interaction between these mountains and valleys. Okay. Initially, they're just settled here, just a normal force. Okay. No friction. But when I go to push on this, that makes the mountains and valleys like push against their sides. Does that make sense? Okay. And I push harder, and the mountaintops are like, push harder, like, push harder, like, at some point, what happens? Does it push on indefinitely, forever? At some point, there's this maximum point. This is known as maximum static friction, maximum static friction. And this is point right before slipping, sliding occurs. It's the point right before slipping or sliding occurs. This is the breakaway point. Maximum static friction is a point right before slipping and sliding occurs. It's the breakaway point. So as I push harder, 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 at some point these break. The mountaintops and the valleys break. So okay. And then at that point, it starts to slide. Okay. And this is known as kinetic friction. So a friction with a subscript K. And this is the friction when surfaces are slipping and sliding. Okay. Kinetic friction is the friction when surfaces are slipping or sliding. See to that? Okay, so now we're sliding across that. Okay, kinetic friction. Now, the equation I gave you at the beginning was the friction was equal to the coefficient times the normal force. I've got different values of what friction can be. So to accommodate for that, we actually have two equations. So maximum static friction is going to be equal to the coefficient of static friction times normal force. And kinetic friction is going to be equal to the coefficient of kinetic friction times normal force. So it's the same format. We just have two different values of coefficients, one for static, maximum static friction, and the other for kinetic friction. But it's the same overall equation. Get to that? That's the deep dive on friction. So let's start applying it. All right, give that one a shot. Back to your neighbor.
Yes, if you're applying force on it's applying more pressure to it, which means oh yeah, yeah. So
Correct answer is? Okay. I like B. If A said the static friction between the floor and the freezer has the potential to act, I'd be okay with that. That'd be a good statement. But this, what A is saying, you're pushing on it, and friction does that. What you're going to end up with is a freezer that's accelerating back towards you. Boy, you better push that hard, because if you don't, it's going to come back at you. Okay? That would be ridiculous. Like, does that make sense? Has the potential to exert more force, but it doesn't. It exerts just as much as you are applying to it to keep it at rest. Does that make sense? Okay. Next question. Have a conversation. Correct answer is? Do you remember this graph here? Kinetic friction is less than maximum static friction. C. Okay. Here's two reasons. First one, mountaintops are pressing together, and at some point they start breaking off. You okay with that? And actually, if you like listen real carefully, you can hear the screams of like all little villagers as their mountain villages get destroyed. Okay? You're like mass pandemonium at a molecular level. You're ripping mountaintops off. This is why your tennis shoes wear down over time. You're leaving molecules of them on the ground. Okay? Once you start slipping and sliding, the mountain and valleys aren't settling down. They're just skipping across the mountaintops. Okay with that? Okay. Notice how it's a little bit wiggly? That's because the different landscapes, like sometimes you're going to go across the Sahara Desert. Other times you're going to hit the Himalayas. Depends on the landscape of the tabletop trash can. Okay. But relatively constant. The other thing you got going for you to make this happen is inertia, is in motion. And inertia wants to stay in motion. So both of those two factors cause your kinetic friction to be less than your maximum static friction. Is that? Talk to your neighbor. Correct answer is? Correct answer is C. And this, there's no speed part of that equation. Once it's slipping and sliding, doesn't matter how fast it's slipping or sliding. The kinetic friction is relatively constant. Good with that? All right. Set this problem up. Free body diagram, some of the forces in X and Y direction. Make it happen. How'd we do? Quick question. Is that going to be static or kinetic friction? Kinetic. There's slipping and sliding going on. Okay. How are we doing there? Doing all right? Okay. Once you have it set up, now we can start engaging with the numbers. Okay. Ultimately, what am I looking for? Acceleration. Where do I find acceleration? Okay. So if I can figure out mass and friction, I'm golden. Okay. Can I take 75 and plug it in for mass? Is that something I can do? 75. Yes. It's in kilograms. I can plug it in for here. Okay. Can I take 0.5 and plug it in for kinetic friction? Can I take 0.5 and plug it in here? If I give you the coefficient, that is this thing. That is not this. Okay. Most of the time, if I give you a coefficient, that tells you that you're going to be employing that equation. Does that make sense? If I give you the coefficient, that's this value. So specifically, it's kinetic friction. Okay. So to find friction, I have the coefficient of friction times normal force. I don't know what normal force is. Where am I going to find normal force? Right over here. Yeah. Okay. So can I take 75 and plug it in here? What do I need to do first? Convert it to newtons using that equation. So I have force of gravity is equal to 75 kilograms times 9.8 is equal to 735 newtons. Good with that? What can I do with that piece of information? Okay. So we find that normal force is also equal to 735 newtons. What can I do with that piece of information? Well, that's going to give me information about that. So now I have kinetic friction is equal to the coefficient of kinetic friction times normal force, which is 735 newtons. And I find my friction to be equal to, is it 367.5? Is that right? 367.5 newtons. what can I do with that? Well, that gives us insight to this. So I get a negative 367.5. Divide that, I get a negative 4.9 meters per second squared. What? So much work. Okay. So we are now incorporating both the X and the Y, like using that to solve stuff. Here's my very strong recommendation. Set it up and be organized. There are a lot of little steps. Each step is easy. Like they're not hard, but they're just a bunch of them. And to be perfectly honest with you, this is a really simple problem. Like it's not very much stuff. You've got three forces and none of them are at angles. But there was a lot of work involved. And it gets way more complicated. Set it up, be organized. Your setup will give you your roadmap. They'll give you a big picture, like looking at the whole thing, like, okay, how do I need to do this? Or like your checklist. Okay? Let's try a harder problem. Oh, yeah. Okay. Pushing a couch up an incline. All right. Before we get too deep into this, what is the minimum force that you need to push? Okay. Phraseology is like, what is the minimum force you need to push, or like what is the maximum angle this could do, or like the couch is about to start sliding, or like the cars just began to skid, or something like that, where it's like building this climax of like whoa, or like this limit is about to start happening. If any of that comes out in the storyline, that screams maximum static friction. Okay. Is that so? Again, if you see anything, any verbiage that says what's your maximum, what's your minimum, about to start sliding, or it's just began to start sliding, what we're going to do is we're going to say that's, I'm being asked to use maximum static friction. And the consequence to that is there's no, at that point, no slipping. Even if the problem says it has begun to start slipping, you say, I'm looking at it when it's maximum static friction, it has not yet slipped yet. Does that make sense? Like how you interpret problems. Okay. So with that information, set up this problem. Free body diagram, some of the forces in X and Y direction, like all out. make up the ramp positive. Make sure you tilt your axis. It's 20 degrees. How do we do? Good with that. Okay, now, probably don't have time to do it all out full on, but I want to give the big picture overall idea. I'll start calculating it, the bell will probably ring. I'll continue to record. You're dismissed after that. But here's the big picture. Ready? What am I looking for? Ultimately, I'm looking for how hard I have to push. I'm looking for applied force. That's ultimately my goal. So in order to find applied force, I need to solve for friction and force of gravity. Okay? Can I take 100 and stick it straight into here? No. I first need to find force of gravity. So that's going to go in there. That makes sense? Once I have that, then I need to do some trig to find FGX. So sine of 20 equals FGX over whatever this is. You okay with that? That gets me that. Then I need to find maximum static friction. This right here is a distractor. There's no relevance to the problem whatsoever. You're using this. I gave you the coefficient. Okay? So in order to use a coefficient, you need this equation. So you've got 0.3 or 0.4, sorry, times normal force. Where do we find normal force? Over here. So I need to find FGY first. So I need to do some more trig. The cosine of 20 equals FGY over FG. I get that, which gives me this. Which allows me to find friction, which allows me to find applied force. Lots of little steps. Please be organized. Okay? I'll fill this out for number-wise if that would be beneficial. You can watch the video. Okay, I got a worksheet due tomorrow. 100 kilograms. This is 9.8. Force of gravity is 980. So you go 980 here, 980 here. So that is 335. So that's 335 newtons there. Have a good day, folks. 0. Okay, we got that. Now we're looking for static friction. So we got coefficient times normal force.
Have a good one.
You too, Grayson. And then that is 921. So that is normal force is equal to, also is equal to 921. And that can be used here. And so your maximum static friction is equal to 368. And then that can be used here, 368. And so your applied force is equal to sum of those. Find that to be 703. And that is how you do that.